For 1.3 notes, we're focusing on when you scale up a recipe and change the units, like from cups to ounces. What are some of the issues you have to deal with? So for vocabulary, some words that we need to know. Look at in the green here. It says part-to-part ratios. Yesterday we were working with part-to-whole ratios, right? In that denominator we had the whole amount of cups, and on the top we had a specific part of it. Over here we have scaling ratios. We're going to focus more on that today. We're going to learn a little bit more in detail about that. And underneath that we also have some conversions, like 1 cup equals 8 ounces. 2 cups equal 1 pint. Where am I? 2 cups equals 1 pint. 1 quart equals 2 pints. 1 quart equals 4 cups. 1 gallon equals 4 quarts. 1 gallon equals 128 ounces. So when we go through this, and I think specifically on the back more, we can use some of these conversions to help us solve what we're working on, okay? So when we go through notes or quizzes or homework, when we're studying for this stuff, this might be a good key to keep so that we can remember those conversions. What do you think? Sounds good? Maybe even highlight it how we have it up here. That might be even better so you can see it clear. But what we're looking at here, it's written kind of small on this page, but on your page you can see it. It says in problem 1.2, you may have used the ratios below to determine which recipe was the most orangey. Below are 2 ratios describing mix A. Do we remember doing this yesterday? We compared the concentrate to the water. So we had like 2 was our cups of concentrate and 3 was our cups of water. And then over here, same thing. 2 cups of concentrate and 5 cups of water. So these would be more of parts to parts, because we're comparing the part of the concentrate to the part of the cup or juice or water, whatever they're comparing. So that would be more like in our green up here, our parts to parts ratio. Down here, we can say that the first ratio is a part to part ratio, like we just said. It compares 1 part, the water, of the whole part, the juice, to the other part of the concentrate. The second ratio is a part to whole. It compares 1 part, the concentrate, to the whole, which is the juice. To the whole, which is the juice. This entire thing is juice. Well, if there's 2 cups of concentrate, then there must be how many cups of water to get that juice? If our whole is 5. 3, exactly. So that's what they mean by that. So for mix B, you can write the part-to-part ratio as 5 cups concentrate to 9 cups of water. That can be written as a couple different ways. We can do 5:9 or 5/9. You can write the part-to-whole ratio as 5 cups to 14 cups of juice. Well, now that's part-to-wholes. We got 14 cups because we added the cups from the first part and the cups from the second part to get our total amount of cups, which they said was 14. So this would be more as 5/14 or 5/14. That's how we compare the parts to whole. Do you see the difference there? So scaling ratio was one of the comparison strategies Sam used in the problem for 1.2. Okay, well here's our 1.2. How could Sam use the ratio to compare mix A and mix B? Let's look at what kind of ratios he had here. 2 cups of concentrate over 3 cups of water. Let's look at that. I'll give you maybe a minute or two with shoulder partners to talk it out and see how Sam could use the ratios to compare mix A and mix B by looking at which ratios. So how can we look at the ratios to compare the scale-up form for mix A and mix B? Well, what's the first form in mix A? What do they tell us? Right up here. Lily? Okay, so I can write that right here. 2:3. Okay, so now it's going to scale up to what? It's going to be 4:6. All right. Well, we're comparing it to our 5/9. Why don't we scale it up again so that our denominators are the same as 9. So this would be 6 colon 9, right? Well, now we compare 6 9 and 5 9s. Can't we?
Yeah.
So we can write here, he can scale up the ratio 2 colon 3 to 6 colon 9, right? 2 colon 3 to 4 colon 6 to 6 9 to make it easier to read or to compare. To make it easier to compare the ratio 5 9. Isn't it easier to compare? We can tell which one's larger and what's going on there. Yeah. So we're going to do the same thing down here. We're going to compare this. You can scale up a ratio. For example, 2 to 3 and 8 to 12 is a scale up. Well, what is it going up by? We're going to try to do that with these down here. We have 4 over 6 and x over 36. What is it scaling up by, right, for number 1 to go from 6 to 36? It's scaling up by 6. What he did was say, hey, this is 6. Okay, I can multiply that by a 6. 6 times 6 is 36. So if I multiply my denominator down here, that's going to give me my 36. And what I do to my denominator, hey, I'm going to have to do it to the top. So if I have 4 up here, I'm going to multiply that by 6. Because I don't know what x equals. Well, when I do that, what do I get? 24. 6 times 24, or I'm sorry, 6 times 4 gives me 24. So right here when it says for the solve for the missing part of each ratio. Well, I found how it scaled up, the patterns that were going on in the denominator or the numerator, whatever way in this form it's written in the denominator. So how is it going up in the denominator? We're going to do that same thing. So for number 2, 9/5 and 4 over x. I have 9/5 equal 4 over x. Well, what is it scaling up by to get from 9 to 45? Robert. It's scaling up by 5. 9 times 5 gives you 45. So since I'm going up by 5 in the numerator, I have to do the same in the denominator. Anthony? So when I did multiply this in the denominator, 5 times 25 would give me what my x equals, which Anthony said was 25, right? One more. I have it written sort of down here a little bit. 12, 4, and x 36. So I would rewrite it like this. If my 12 is first and my x is first, those both have to be on the top or bottom. I have to keep them on the same side. Do you see how we did that? Since my 4 and 36 are written last, whether it's on the top or bottom, they both have to be on the same side. Well, we put them both on the bottom. You have to make sure that's like that. So what are those scaling up by? 4 to 36. I'll give you a minute to determine what are those scaling up by. How do we get 4 to 36? Okay, so what did we find the scale up for this one is? What did we determine? Times 9. Exactly. 4 times 9 would give me my 36. Okay, well, if I did that in the denominator, I got to do it to my other side, so I have to multiply that by my 12. 12 times 9, Lily? 108. 108, which is what my x would equal. 108. Any questions as to how we got those? No? Okay, for part A, it says, a typical can of orange juice concentrate holds 12 fluid ounces. The standard recipe is shown below. Okay, so mix 1 can of concentrate with 3 cans of cold water. So how many cans do I have total? How many cans am I using to get one form of recipe? 4? Exactly. So we have a total of 4 cans that we're working with. Well, in question 2, it says, how large a pitcher will you need to hold the juice made from a typical can? Well, here's my typical can. And how large of a pitcher will I need to hold all the juice? What do you think? How would we do that? Lily? Why would we do that? Make sure we're listening. So she said, well, in one can, they told us there's 12 fluid ounces, right, Lily? Good. Okay, well, we have 4 cans for one batch. So, how many fluid ounces would that be? We take the amount of fluid ounces for one can and multiply it by the amount of cans we are using, which we set up here. We added it up to be 4. So Lily said she came up with the answer of 48. Thumbs up? You need help? Oh, okay. All right. Okay, so if we go on to the back page, this is very similar, but now we have it written a little different. A typical can of lemonade is still 12 ounces, 12 fluid ounces. One can of lemonade holds 12 fluid ounces. The standard recipe says 1 can of concentrate with 4 1/3 cup of cold water. All right, well now we're working with a little bit funkier of a number, aren't we? Okay, how could we do that? 1 is a whole number. What is our total? So I'm basically adding that, right? I want to find my total amount of cans. Well, I have 1 can and I have 4 1/3 can. And so what do I get when I do that? Robert? 5 1/3. I just add my whole numbers. 1 plus 4 gives me my 5, and I'm just going to bring my 1/3 with it. So 5 1/3 cans total. So now they're asking us the same question. How large a pitcher will you need to hold the lemonade for a typical can? Well, there's the formula for my typical can. They stated that that's what I'm going to use. A total of 5 1/3 cans. So Robert, what am I going to do? 12 times 5 1/3. Exactly. And why did you do that? So we know we have a total of 5 1/3 cans. And we have to multiply it by the amount of fluid ounces in 1 can. So when I do that, what do I get?
60 1/3.
I'm sorry?
60 1/3.
Can we convert it so we can get rid of that 1/3 so we can get a whole number now? 64. How did you get that? What did you do? Divided by 30? Oh, divided by 3. Okay. Gavin, did you do it differently?
Yeah, I did 1 divided by 3, and that was 0.333. So I did 12 times 5.333.
Okay, so you made it a decimal. So those are both ways that would work. Gavin did 1/3. He saw that 1/3 is 0.3 repeating. So when he multiplied it, he did 12 times 5.3. And how did you say you did it again? You did 12 divided by 3, and then what did you do from there? 12 divided by 3, and then you added... Okay, you added that to 60. Exactly. So she did 12 times 5, which gave her 60. And then she saw that 12 divided by 3 is 4, so she did 60 plus 4 to get her 64. Exactly. So Sam and Gavin both found two different ways to do it, which is completely fine. We still get to our amount that will hold in the large picture, which is 64 for this. All right, so let's go down here to 2. I'm going to let you work for a minute with some partners. It says the pitchers below hold a half a gallon, which is this like dark purpley pink one. Everyone sees that? That's our half gallon. 60 ounces, which is this orange one we have. And 1 gallon, which is this one big one in the middle. It's like a greenish yellow color. Which container should you use for the lemonade from 1 can? Well, we know how much is in 1 can in ounces. And we know which ones we have here. We have a half gallon, a gallon, 60 ounces. And we can probably use our equations that we had on the front page, right? To convert some stuff from gallons to quarts to ounces, whatever we have to do. So use those equations, those conversions that we have on the front to help you to figure out which container would best fit to use for a lemonade of 1 can. Okay, can I give you like 2, 3, 4 minutes? Does that sound okay? Okay. So, for question 2, which container should we use for lemonade from 1 can? Well, we found in question 1 that for a typical 1 can, how much is held in it? 64. So that's what we're looking for. That's what we're aiming to get for question 2. Which one of these would be best to collect 64 in it? Maria? The half gallon? Why did you say that? Exactly. So she said 1 gallon equals 128 ounces, which, yeah, that would work. Okay. I mean, our container would be a pretty large. We'd only half fill it. But if we look at a half gallon, you found that conversion on the top of our front page. Remember I told you maybe highlight it so you can see it clear? Well, half of 128, you said, Maria, was 64. And that's what we need. That's what we're looking to get. Well, our 60 ounces, it's too small right off the bat. We would overflow it. So we already know, because we're looking for 64. 60 is too small. So now it's between a gallon and a half gallon. Well, they would both work, but a half gallon would be the perfect amount for us to use. So we would prefer to use the half gallon since it's 64 ounces. Aiden, do you have a question? Okay. Yeah, Blake? I'm sorry? The 60 ounce one would be too small. If we were to fill 64 ounces into a 60 ounce, like a vase, it would overflow, wouldn't it? So we can eliminate that one. We don't want to use that one. What about question 3? It says, the recipe is written using cans. Could we have written the recipe using fluid ounces? Explain. Write the new recipe using fluid ounces. Well, what could we do here? Well, how much is 1 can? They want us to convert it from cans to ounces. 1 can is how many fluid ounces? Yeah, they told us that it is 12 fluid ounces. All right. So what should we do from here? Can we see that 1 colon 12? Oops, that should be 12. Let's look at this. If you look up here, is it on the top of this page? Yes, it is. Look at it in that lemonade. Mix 1 can of concentrate. There's my 1 can. And then they say 1 can, or 4 1/3 can of, what is it, the cold water. So there's my 4 1/3 cans of cold water. Okay, well now this is cups, or can, I'm sorry. This is cans. And I'm basically converting it into my fluid ounces. Do we see that? This left fraction This left ratio, 1 over 4 1/3, is written as cans. Right here. And then this is written as fluid ounces. But we want to find the total as fluid ounces. So what is the scale-up factor? How would we determine it? What is the scale factor from 1 to 12? I'm sorry? It is 12. So if we multiply that by 12, we can multiply this by 12, couldn't we? Okay. So when we do that, what happens to our water, our cold water? We know that the concentrate is 12. Well, what's the fluid ounces for our cold water? How could we calculate that? Lily?
Is it 16?
Not quite. I'll give you maybe like a minute or two. Talk it out. Try to problem solve. Do you have a...
Yeah, I have it, but with my calculator, I'm actually typing fractions and stuff.
Okay, so you can actually type in fractions on that, Brayden?
Yeah, I got 62.
You got 52?
Yeah.
Okay.
How do you type in fractions?
So, this is written as like a fraction. 4 1/3. Well, we know how to write in a fraction on a calculator, can't we? If it's just, say, 1/3. Couldn't I put that in parentheses on my calculator? On my calculator, I can change this to write 1, 3, enter. And that would give me 0.3, repeating, right? Well, Brayden can do it on his calculator. We're going to use these other ones. How do we get this as a mixed fraction? 4 1/3. Let's write it as a mixed fraction, and then we can put it in parentheses like up here. 4 1/3 is what? As a mixed fraction? Anyone?
4.2.
We multiply these and then add it up here. So 4 times 3 is what? 5. And then plus another one. This is 4 and 3, I'm sorry, is 12. Why did I say 5? 12. Oh, maybe that's what I said. So 4 times 3 is 12, and then we're going to add another one to it to get 13. So this is really, we could write it as 13 over 3. Okay, so why don't you put that in parentheses in your calculator, and then just multiply it by 12. Okay, so I will give you a minute just to practice that on your calculator so you can see how that works. So now we see when we practice it on our calculators that if we were to multiply this, 13 over 3 times 12, that would give us our 52, which is what it would be under my x equals 52. That's how many fluid ounces it would be, which is what we're converting it from. We converted it from cans, my 1 over 4 1/3, to my fluid ounces. Any questions as to how we did part B? No? Let's go on to part C then. Cece is making orange juice using 16-ounce cans of concentrate. She's using the standard ratio of 1 can of concentrate to 3 cans of cold water. Okay, how many cans is she using? 1 can, where is it? 1 can, 2, 3. So we're using 4. Exactly. 4 cans total. 2. Okay, I heard. Isabel, did you say that already?
Yeah.
So how many cans will she use total? Well, they said they wanted 16 ounces. So let's do our 16 ounces times the total cans that we are going to be using for one form. For one recipe, I guess. Well, we're using 4. So 16 times 4, which gives me what then, Isabel? 64 ounces total. No, not right now. I recommend that you label, but some of these we didn't, some we did, so it's okay. As we go on, we will focus on that. I'll specify for the quizzes. Olivia has 1 gallon pitcher to fill with orange juice. She uses a standard ratio of 1 can and 3 cans. So we know we have 4 total, and we can figure out how many fluid ounces is in 1 gallon pitcher, can't we? How many is in 1 gallon? Well, we know that 1 gallon equals 4 quarts. This is written on the front in those conversions. Well, now let's get this into cups because that's what they have. They have 4 cups, right? So let's get our conversions into the same, both into cups. Well, now we can go from gallons to quarts. Okay, so let's go from quarts. 1 quart equals, how many does 1 quart equal for cups?
4 cups.
Yeah, 1 quart equals 4 cups. So if I have 1 gallon, how many cups would I have total? Using those conversions.
6 quarts. Cups.
How many cups would I have total? Not quite. 32. Who said that? Lily? So how did you get that?
Well, I did it different ways. So I did the 128 for the
Which is 1 gallon. 1 gallon is 128. Okay, and then what did you do?
divided it by the 4 because the
That's the amount we have total.
I divided that, I got 32.
Okay, so she took the total amount of cups we have, divided by, this is fluid ounces, right? Or 128. So 1 gallon, she saw in fluid ounces equals 128. So we could do that and divide it by 4 because that's the total amount of cans that we have. We have 4 cans total, right? 1 plus another 3. And you said you got 32 fluid ounces then of the concentrate. That works. Does everyone see how Lily did that? So let's work on 2, this last one real quick. Charles has some leftover cans of lemonade concentrate in his freezer. He didn't use all of it from before. He uses 1/2 10-ounce can of concentrate and the standard ratio of 1 can to 4 1/3. How large of a pitcher does he need? Times what? 1 1/2? Not quite. Let's write this out. 1. This is the 5 1/3 that you saw, right? Because we have 1 and our 4 to get our 5, like we did above in question, right at the top of the page in part 4. We found that it equals 5 1/3. Well, there's 1 conversion, and we're trying to get it to 15. When we convert that, it scales up to what? It scales up 15. Yep. So we do that. And what we do to the bottom, we have to do to the top. So right above in question 1A, I'm sorry, what is it? 3, we're going to have to do that same kind of multiplying down here to figure out what X is. It scales up by 15. I'll give you about 2 minutes to determine what our X would be here. No. Okay. 80, right? When we multiply it, 5 1/3 times 15. We can do it, divide it, and then multiply. Who said 80? Was it Brayden? Okay. Yeah. So when we get it, our X equals 80 ounces. And here is our homework. Oh, I'll write it for you. Page 23. 13, questions 13, 15, and 17 on page 23. That is our homework. That is due tomorrow.